7.4, I just want to make sure that you've seen it. Oh, and I guess we don't want to be doing Science 9. Let's go to Chem 11, and let's go to Stoich, and let's turn on the projector. There we go. What is that? No, you aren't yourself. Oh. Okay. Chem 11 stoichiometry 4. Okay. No, I think this was my grade 9s that got stuck in here by mistake.
No horseplay?
Yeah.
No touching others? What?
It's like safety.
Oh.
Right? Fire extinguisher, fire blanket. Do not eat or drink. Anyway, it got stuck in your guys' class by mistake. Oh well. Anyway, this was for my grade 9s, but it's not there. Anyway, so we wanted to go to here, and I wanted to go to 7.4a, and let's just make sure, which is on page 80 in your previous book. And if you don't have it with you, it's okay. We're just going to briefly go through things. I assume that some of you have already done this over the weekend. Okay, so if you are in that boat and you would like to just work on the practice, you can go ahead and do that. That's on page 85. But I just want to go through a few things today to make sure that you feel like we've actually learned it. So, in this particular example, we have our heat term here, okay, and our delta H is negative 91.8 kilojoules per mole. And that per mole means per 1 mole of the reaction, which means whichever thing in the reaction has a coefficient of 1, that's how much you get for 1 mole of that one thing, okay? So for this particular reaction, you get 91.8 kilojoules produced for every 1 mole of N2. Yes? You get 91.8 kilojoules produced for every 3 moles of H2. Yes, and for every 2 moles of NH3. So it essentially just works like everything else in stoichiometry. Yes, it's just instead of having a 1-to-2 ratio, it's a 1 to 98.1, or sorry, 91.8 ratio. Yes, so you could write these ratios. You can say, for every 1 mole of N2 used up, I get 91.8 kilojoules of energy produced. For every 3 moles of H2 produced, I get, or used up, I get 91.8 kilojoules. Yes? And you can do calculations with that, just like any other calculation. So if you start with 5 moles of H2, you say, I have 3 moles of H2 for every 91 kilojoules. And we are asked to find the change in enthalpy here, change in enthalpy. So because that is the case, we're going to say, okay, the change in enthalpy is negative 91.8. So we're going to get negative 153 kilojoules. And so our delta H then is equal to negative 150 kilojoules. And this is not kilojoules per mole anymore. This is just kilojoules because the per mole went away. Yes? Okay. So from now on, I am going to get sticky about kilojoules or kilojoules per mole. All right? Now, this is our change in enthalpy, and change in enthalpy is either positive or it is negative. But if I ask you, instead of the change in enthalpy, if I say how much heat is released, You will not say, I released negative 150 kilojoules. That doesn't make any sense. The released part is taking the place of the negative sign. Yes, the negative sign is because we're looking at what was the change. When we say how much was released, we're going to give the absolute value. Yes, because it doesn't make any sense to say I released a negative amount of heat. That's just nonsensical. Yes? Okay. Okay, so there was that bit. You can do other calculations, just like, with all our other ones. If you have grams, you would convert. Oh, why does that say gram moles? Fix. Thank you. Well, okay, there we go. You can convert it to moles, and then you've got 98.1 kilojoules per 1 mole of N2. And in this case, it asks you how much energy is given off. And so you would say, I'm going to take that negative number and turn it into the absolute value, which is just 729 kilojoules is released. Okay. You can also be given kilojoules and asked to find something else. In this case, you're given 558 kilojoules. We know that we have 180.6 kilojoules per mole, which means per 1 mole of N2 or per 1 mole of O2 or per 2 moles of NO2. Yes? Okay. So per 2 moles of NO2, and then you can find your mass and et cetera, et cetera. So that's that. There's nothing else more to it. It's just like regular stoichiometry, just with fancier numbers. Yes?
Is it NO or NO2?
NO, just NO. Sorry, I probably said NO2 because NO2 is much more common than NO, but I meant NO. Okay. Now here's the thing. If you change the coefficients in a chemical equation, the delta H changes proportionally. So if we multiply an entire equation by 2, what happens to the delta H? We multiply by 2. If we divide our equation by 2, what do we do with our delta H? Divide by 2. So if we have this reaction here, if we divide 2 by 2, we get 1. 2 by 2, we get 1. And 1 divided by 2 is a half. What would delta H be for this reaction? How would we calculate it? 566 divided by 2, which is going to give you whatever it gives you, kilojoules per mole. I'm not even going to bother calculating it because we can do that some other time. And if you divide it by 2, oh, here it is. There we go. Divide by 2. I don't know why this is sideways. That's really irritating, but that's okay. All it says is that if you reverse a reaction, what would happen to the sign of delta H? It would flip. So because this one, delta H, is equal to positive 283 kilojoules per mole. If we wrote it backwards, CO plus 1/2 O2, that would go to CO2 plus 283 kilojoules. So our delta H would be negative 283 kilojoules per mole. And of course, you can both multiply it by 2 and switch it around, or, various things like that. But that's it. I would suggest that if you want some good review, there are some questions in enthalpy and limiting reactants. So it reviews limiting reactants for you, but it also does things like practice rewriting the equation with the heat term. So if you've forgotten about any of that stuff, there's a little more practice there. Yes? So part of your homework for tonight will be 7.4a and 7.4b. If you've not done them, just do enough to feel good about them. Okay? 7.41, 4a, and b. And with that being said, we are going to move on to solutions. And we are going to talk about, why is this all blank here? That's okay. Oh, I bet I know what I did. I have no idea. Okay, life is weird, but that's okay. There we are. We did look at this last day, did we not? Okay, that's what I thought. Okay, so we have strong acids and weak acids. Could you remind your partner or your neighbor what is a strong acid?
They just some parts.
So what is a strong acid? Yeah, it's an acid that dissociates completely, okay? So if I was to take some HCl gas and I were to dissolve it in water, I can think of it like it's a two-stage process, even though it's really only a one-stage process, okay? Like it really happens all at once. But we can think of it like a two-stage process. So we have HCl gas, and we dissolve it in water. And we get HCl aqueous. And that would be step 1. Step 2 would be that the HCl would then dissociate 100%. Yes? And we would end up with all of it as H plus aqueous plus Cl minus aqueous. So that's a strong acid. And that means that all of the acid has turned into ions. And so therefore, this would be a very strong what? Electrolyte. So we have lots of ions. And therefore, it is a strong electrolyte. Now, the counterpart to a strong acid is a weak acid. Yes? Why does it not want to just stop getting bigger? Okay, weak acid. It's an acid that does what? Yeah, it dissociates only partially, okay? Acid that dissociates only partially. And this one does actually kind of go through a two-step process, okay? I mean, I guess maybe the strong acid does as well, but it happens so fast that it might as well be all happening at the same time. So we might have HF which is a weak acid, and we dissolve it in water. And that's step 1. And we get HF aqueous. What is that process where we just change the state, but it doesn't break apart? That's dispersion. Okay, so we get the dispersion of the weak acid. And then, how do we write the arrow for a partial dissociation? We have one half of the arrow going this way and the other half of the arrow going the other way. We sometimes call it like a double harpoon, because like harpoons have that kind of like spear shape just with the hook on one side. Okay, and then we have, and I'm going to write these small because we don't have very much of them. Okay, we have H plus and F minus. That's aqueous, and that is aqueous. And that is our partial dissociation. Which side do we have more of, the HF together or the H and F separate? HF together. HF together. There's lots of this. And we have only a little of those guys. And if we have only a little, what can we say about it in terms of being an electrolyte? It is a weak electrolyte. And then finally, we might have something like an alcohol. And let's say we had CH3OH, and it's a liquid. And then we dissolve it in water. What happens? Does an alcohol dissociate? No. So it just stays as CH3OH. Is good? Okay. And this one, we just have the dispersion and there's no dissociation. And so this, what type of electrolyte is an alcohol? It's non-electrolyte. Excellent. Okay. So let's then go to, is it here? Okay. So let's go to page 17. Because I want to talk about the difference between strength and concentration, which are different. Yes? Strength is how much the acid dissociates. Whereas concentration is how much acid there is in a given volume. And that what that would be, how much acid would be measured in moles of acid per liter. So we're going to look at a few instances here where we have, for example, a strong acid, and it is also very concentrated. So we have lots of acid molecules, but they are all dissociated, 100% dissociated. So it's a strong acid, 100% dissociated. So if we look, how many of the things in there are ions? All of them. And since we have a high concentration of ions, that means that our conductivity is high. But if we take a weak acid at the same concentration, okay, they're both concentrated, so they have a high concentration. Even though we have lots of acid particles, how many of them are dissociated? A few. And if the concentration of the ions is low, what happens to our conductivity? Low. Conductivity is low. Now we're going to take that same strong acid and we're going to dilute it. We're going to take the same weak acid and dilute it. So now, instead of having concentrated solutions, we have dilute solutions. So we look at our strong acid, and lo and behold, even though it's a lot lower concentration, we still have a medium amount of ions. Yes? We have a medium concentration of ions, therefore the conductivity is medium. And it might still, even if I hadn't diluted it this much, it might still be a high conductivity. Do you know what I mean? Like, it just depends on how diluted it is. Because if you remember, do you remember from last day when we had like the 1 molar and then we used the 0.1 molar and it was still pretty darn bright. It was almost hard to tell the difference. I don't know, was this the block where I diluted it another 10 times or was that my other block? Yeah, I diluted it so it was 0.01 molar in the other block, and it did finally get a bit dimmer, but it took like 100 times dilution to make that happen, right? So it has to get quite dilute in order for the conductivity to drop significantly. And if we have a weak acid, do you remember what happened when we went from the 1 molar acetic acid to the 0.1 molar? What was the 1 molar like? The 1 molar was we had a light bulb and it was fairly dim. But then we had the 0.1 molar. And what happened with the light bulb then? Do you remember it? I had to put it in and like really nothing happened, and then I shook it around a little bit to get the particles moving a little bit more, and so they were bashing into each other a little bit more, and then and only then did we get like this very faint glowing of the light bulb. Yeah? So, and you can see here, how many ions do we have? Hardly any. No, we don't have 5 ions, we only have 2. 2 out of the 5, 2 out of the 4 are dissociated. And so the conductivity is very low because we have a very small number of ions. If a strong acid and a weak acid are at the same concentration, the strong acid will have many more ions, and so it will conduct electricity much better. Therefore, strong acids are considered strong electrolytes. Weak acids are considered weak electrolytes. Nobody is going to ask you something stupid like, if you have a really dilute, strong acid, is that still a strong electrolyte? Nobody's going to ask you that because that's just a goofy question. They might ask you, is it completely dissociated? Will it conduct better or worse than a more concentrated or less concentrated solution? You might get comparative questions like that, but no one's going to ask you, is a dilute strong acid a strong electrolyte? That's just a dumb question. That's a semantics game. Do you know what I mean? I might say, you have a dilute strong acid and you have a concentrated weak acid. Is it possible for them to have the same conductivity? And you might say yes. It would depend on how much you manage to dilute the concentrated acid, the strong acid. Did that make sense? Okay. But yeah, just don't worry about silly things. Bases. How do you know you have a base? OH. So strong bases are ionic compounds that contain OH minus. And because they are ionic compounds, they will be strong electrolytes. Now, their conductivity and their ability to act as an electrolyte does depend on their solubility. But I don't want you to get too wound up about that at this point, okay? If I tell you it is soluble, then you just go, okay, it's soluble. Yes? Not all metal hydroxides are soluble, but we know that all of the alkali metal hydroxides are soluble. So these guys here, 100% soluble. Now, these other ones, this BA, SR, CA, SR, and BA, these guys here, your alkaline earth metals, CA, SR, and BA, they are somewhat soluble, okay? You're not going to worry about that, what somewhat means at this point, quantitatively. You're just going to be like, okay, they're somewhat soluble. So if I tell you that you have made a 0.02 molar solution, you can assume that all of that dissolves. Yes? Because if you have made that, you have dissolved that much. Okay, you don't have to worry about how much will dissolve. We'll worry about those numbers in grade 12. Yes? But just be aware that these guys are also electrolytes. But if I give you aluminum hydroxide has a very low solubility, and I would have to tell you that at this point. Yes? That it has a very low solubility. So it's not like it would be electrolyte, it just wouldn't even dissolve, right? It's not like it disperses, it just doesn't dissolve. Yeah? Okay. So don't really worry about that too much, other than knowing that metal hydroxides are strong bases and they dissociate. So you end up with LiOH, and if you have CaOH2, you will end up with 2OH. So if I had, maybe with calcium hydroxide, I can't make a super concentrated solution, but maybe I can make an 0.01 molar solution, which means calcium would be 0. How much molar? 0.01 molar, and hydroxide would be 0.02 molar. And I might not be able to make a 1 molar solution because it might not be that soluble. Lithium, on the other hand, maybe I can make a 1 molar solution, which means I would get 1 molar lithium and 1 molar hydroxide. Okay. But basically, if you have a strong base, it's a good electrolyte. You have to, oh, look, we have a wonderful word here. Have you guys heard this word, plethora? A plethora. It means the same as a myriad. Ooh, do you know that word? No? Okay, these are both words that mean the many, 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 many free-floating ions. Okay, so if you have a plethora of things, it means you have a lot of them. Okay? If you have a myriad of things, it means you have many, many, many of them. I remember learning these words in grade 10. I had an English teacher who was like cool vocabulary words. So I was like, oh, cool, that's nice. Anyway. And the interesting thing about myriad is you can use myriad as either a noun, like here, plethora is being used as a noun, yes? We have a plethora of free-floating ions. We have a whole bunch of free-floating ions. You can also say you can have a myriad of free-floating ions, lots and lots of free-floating ions. But you can also use myriad as an adjective without the of. You can just say, I have myriad free-floating ions, which sounds kind of cool, I think. Anyway, but you're allowed to do it either way, with the or with the of and without the of. So the of is optional. Anyway, you probably didn't want to know that. You're like, I'm taking chemistry, not English, but I like that word, so you're going to learn it today anyway. Okay, bases. You have to be able to tell the difference between a strong base, in other words, a metal hydroxide, and an alcohol, because they behave differently. Strong bases are electrolytes. Alcohols are non-electrolytes. So here is our base, which we have our metal cation or an ammonium ion, and it bonds with a hydroxide anion. And you can see here we have the hydroxide anion. How is that different from this group over here, which is part of the alcohol, which is not a hydroxide ion, it is a hydroxyl group? How is that different? Yes. Yeah, here we have a covalent bond. These electrons are shared between carbon and oxygen. But those same electrons on the left-hand side of the oxygen, if we look over at sodium hydroxide, these belong only to the oxygen, not to the sodium. Is good? Okay. And because we have those ions, they can be split apart by water getting in between, like the water. Do you remember seeing that video where the little water surrounded the particles? Did we do that one? Did we watch that? Or was that my grade 9s? Trying to remember. We don't know. Okay, that's okay. I'll show it to you later because I know there's some videos I needed to show you. Anyway, they can't do that with this. So the upshot of this is that bases are electrolytes, and you can see that the hydroxide comes off. But alcohols, non-electrolytes, they just stay the same and they disperse rather than dissociating. So bases are strong electrolytes, strong bases. And alcohols are non-electrolytes. What do you think weak bases will be?
I think my friend left this water bottle here. Looks like a green Gatorade bottle.
Anyone see a green? Oh, there it is. Back table there. You're a good friend. What do you think a weak base is in terms of being an electrolyte? Weak base. You're welcome. Strong bases are strong electrolytes. Alcohols are non-electrolytes. What do you think a weak base is? It's a, what kind of electrolyte? Weak electrolyte. Okay? That's all you need to know about it. Okay? Weak bases are weak electrolytes. So we're now going to talk about them a little bit more, but you're not going to get worried if you don't understand it. Okay? You're going to be like, okay, I'm getting a preview of what we're going to do next year, grade 12. Okay? Because I'm going to tell you right now that NH3, do you guys know the formula or the name for NH3? Who is that? That is ammonia. Ammonia is a weak base. Which seems really weird because what does ammonia not have? That bases, as far as we know so far, what do bases have? They have OHs. Does NH3 have an OH? No. However, if you put it into water, water does have an OH in it. What it requires for it to happen is that the hydrogen from water needs to say, hey, I would rather hang out with nitrogen. And so this hydrogen is going to grab onto these two electrons and share them with nitrogen. Yes? And it is going to leave these two electrons behind. Okay, so it's going to say bye-bye to the electrons it's sharing with oxygen. Do you see how those electrons are now oxygen's sole possession? Okay. So now we have OH minus. Oh, look. And if we have OH minus, that thing is going to turn phenolphthalein what color? Pink. What's it going to feel like? It's going to feel slippery. What's it going to taste like? I don't know. Bases taste bitter. Okay? And if you're like, what does bitter taste like? Coffee is bitter. Beer is bitter. Some herbs are bitter. Okay, like if you've got, like there's some lettuce, like, I don't know, my parents would grow lettuce. Usually grocery store lettuce isn't very bitter, but the lettuce my parents grew was sometimes bitter. Okay, I don't know. And if you're like, I don't know what bitter tastes like, you can go home and just try a little bit of baking soda. It will taste bitter and a little bit salty because of the sodium. Okay, but baking soda is a base. Don't try like Windex because that'll make you ill, even though it is a base also. Okay, so at any rate, when you put ammonia into water, we get the transfer of an ion. You are not responsible for knowing how this works this year. Next year, we have a whole unit devoted to the fact that hydrogens transfer from one thing to another. But all you need to know this year is that weak bases are weak electrolytes. So here we have a strong electrolyte. You'll notice everything is ions, all ions. And so we get a good conductivity, and the light bulb is bright. Here we have a weak electrolyte where we have very few ions. Most of the acid is undissociated. And so our light bulb is dim. And then finally, we have a non-electrolyte where none of it dissociates, and so there are no ions, and so the light bulb is off. Yes? And then we've got some exercises here, which we're not going to do right now. Not going to do that. This is what we're going to do. For the next little bit, you're going to get yourselves into groups of 3 or 4 or 5. Okay, 3 or 4 or 5. And if you are in a group of 4, you're going to sit across from each other like this. If you're in a group of 5, you're going to sit across from each other and then put one person on the end of the table. And if you're in a group of 3, you're going to sit 2 people beside each other and one person across from them, like in the middle. Okay, that's how you'll get the best talking done. And you guys are going to read the cartoon aloud to each other. You can either assign one person to be the reader, but I think it would be more fun to take turns and less tiring. And once you are done with the reading, all of you together are going to answer the questions. Make sure that you're not working ahead of your group. Okay, make sure that you all check your answers with each other to make sure that you get it. Yes? Are we good? Okay. Get yourselves into groups. If you find you cannot find a group of 3 or 4 or 5, I can help you find a group of 3 or 4 or 5.
That was it. All right, so.
Just like you said, time like this side of the classroom.
Okay, they have 4.
One of us thinks
Yes.
reading. Not all that.
They have 5.
Yeah.
Okay. If you guys want to work all together, you can, and if you guys want to work all together, you can. Just all squish onto here. Okay. And you guys will find this.
Yeah, but she was
Story time now.
And then the global gases are off this outside.